we're going to be doing is we're going to be making progress towards this demonstration that finite state automata and regular expressions are equivalent models of computing. Any language that I could represent with a regular expression, I could also represent with a finite state automaton and vice versa. We're going to be making more progress towards that, but we're not quite going to have all of the mechanics that we need just yet. We're going to get close. Today, we're going to be talking about two main topics. The first topic we're going to be talking about is we're going to talk more about closure. So that is, we're going to show what sort of operations can we do to languages, such that if we started with a language computable with a finite state automaton, we'd end with a language computable with a finite state automaton. And then we're also going to be talking about this idea of non-determinism. You can kind of think about this as a superpower that we could give to models of computing. Basically, we're just like, we're not going to care about what physics says anymore. We're just going to do whatever. And the idea of this non-determinism is a more relaxed model of what machines can do, what finite state automata can do. And in particular, it allows us to do several things at once. So this idea of non-determinism just means we're able to do several things at once. This is useful for kind of modeling parallel computing, and also for modeling quantum computing. Parallel computing and quantum computing both behave in kind of non-deterministic ways. We often think about them like that anyway. But the idea of non-determinism we're going to see is that we're going to say that instead of your computer just doing one thing at a time, it's able to do many, 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 many things at a time. We're going to define that a little bit more precisely later in class today. So last class we talked about regular expressions, where a regular expression was some way of describing a language by basically giving a pattern for all of the strings in that language. So any string that matched the pattern, we said belonged to the language. Strings that didn't match the pattern, they didn't belong to the language. So in that sense, that's how regular expressions are kind of a model of computing, because they tell us which things are and are not in some language. And we know that there is kind of this relationship between functions and languages. Our regular expression had several different pieces for things we could include in our regular expressions. We had the empty string. So we were allowed to talk directly about the empty string using either double quotes or this epsilon character that looks like a backwards 3. We could use literal characters, so that is things from our alphabet. So characters from our alphabet could be included in our regular expressions. We could have alternation or union. So that is this vertical bar which says the first thing or the second thing. So it can match either the first regular expression or the second regular expression. We had concatenation, which says that the string needed to be composed of two pieces, where the first piece matched the first regular expression, the second piece matched the second regular expression. And then we had this Kleene star, where we said you can take 0 or more copies of some regular expression. For a string to match a regular expression with a Kleene star, we need to be able to break it up into as many pieces as we would like, where every single one of those pieces matches that regular expression inside the star. So our ultimate goal right now is to demonstrate this proof that as a model of computing, finite state automata are equivalent to regular expressions. So we've shown proofs like this before. We've shown proofs of this format where I've got two models of computing and I want to show that they're equivalent. So for instance, we said that we had, if we had and or not circuits compared with NAND circuits, we show that those were equivalent models of computing. How did we show that? Yeah, so basically we showed that we could take anything that we could do in one model of computing, and we could sort of translate it into this other model, such that the functions that we computed were going to be the same in the pre-translated version and the post-translated version. Basically, we show this by providing some sort of mechanism for translating model A into model B. So that's what we're going to be doing in order to show that finite state automata, as a model of computing, are equivalent to regular expressions. They have equal power to regular expressions. Is we can show any finite state automaton can be translated into some regular expression for the same language, and any regular expression can be converted into some finite state automaton for the same language. If I did that, then we could conclude finite state automata are equivalent to regular expressions. So if I wanted to show that regular expressions were at least as powerful as finite state automata, so kind of the power of a regular expression is greater than or equal to finite state automata, then that means that I need to be able to show that I can take any finite state automaton and translate it into a regular expression. If I could take any finite state automaton and translate it into a regular expression, then that means anything an automaton could do, a regular expression could do. So regular expressions must be at least as powerful. So if I could translate a finite state automaton into a regular expression, that says anything a finite state automaton can do, a regular expression could do as well, so regular expressions are at least as powerful. We're not going to do this in class. I'm not going to ever expect you to implement something like this or be able to do this by hand or whatever. That's because it's tedious, it requires a lot of legwork to get there, and it's not actually super useful in application to go in that direction. It's very, very rare that in application anybody ever goes in that direction. So I'm just going to skip it, but I'm going to tell you that textbook theorem 9.12 demonstrates that for you if you care to see it nonetheless.